Swayam Prabha. Digital India. Educated India.
Hello and welcome. A little recap on what we have been doing in splines. First, the definition. An nth order, which is an n-1 degree curve, a spline, is Cn-2 continuous everywhere in the domain of definition. That is, in the domain of t, going from minus infinity to plus infinity. Now, this definition is something that we will be keeping in mind throughout our discussion on splines. In previous lectures, we had seen how to construct bell-shaped B-spline basis functions through polynomial splines. You would agree with me that the mathematics was quite involved and tedious. We both figured that it was probably not a good idea to continue constructing basis functions using polynomial splines, and we are looking for alternatives. Here, with regard to the basis functions, let me revise a few things. Number one, note that this bell-shaped piecewise composite basis function is not a single curve. It is composed of 4 segments. So this is a cubic spline, and that's the reason why it's composed of 4 individual segments. Each segment is a pure cubic polynomial by itself. These here are junction points. At these points, position, slope, and second derivative are continuous. Any curve for which these conditions are not there will not be a spline. Let me rephrase. Any nth order or an n-1 degree curve which is not Cn-2 continuous will not be a spline. Too many negatives there. Let me come up with a third statement. A spline of degree n-1 has to be precisely Cn-2 continuous in t ranging from minus infinity to plus infinity. Today we will see how to construct B-spline basis functions using the Newton's divided difference approach. So let's start with the algebraic form of the Newton's divided difference approach that we had seen in the previous lecture. This is a little revision for you. So y of xj plus 1 up till xj plus k within square parenthesis. Now this notation is something that we have seen represents the divided differences, can be written as summation r goes from 0 to k of y sub j plus r over w prime x sub j plus r. Can you tell which divided difference would this expression represent? Now when k is equal to 0, we have y of xj, that is the 0th divided difference. When k is equal to 1, we have y of xj plus 1, that is the first divided difference. So this notation here represents the kth divided difference. In this expression on the right hand side, wx can be constructed as x minus xj times x minus xj plus 1 up till x minus xj plus k, and w prime is the first derivative of w with respect to x. W prime of xj plus r is simply this expression evaluated at xj plus r. To revise, let's test again whether this expression holds good. For k is equal to 0, we have y of xj equals y of xj over w prime xj, which is simply yj. In this case, we have w of x equals x minus xj, so w prime is 1. For k equals 1, we have the first divided difference with base as xj, so y of xj plus 1 equals, from this relation here, y of j over w prime of xj plus y of xj plus 1 over w prime of xj plus 1. Here w of x equals x minus xj times x minus xj plus 1. So w prime, the first derivative, is equal to x minus xj plus 1 plus x minus xj. If you plug in xj, this expression goes out. So we have xj minus xj plus 1. If you plug in xj plus 1, this expression is 0, and we have xj plus 1 minus xj. So y of xj plus 1 equals yj over xj minus xj plus 1 plus yj plus 1 over xj plus 1 minus xj, which is equal to yj plus 1 minus yj over xj plus 1 minus xj. This is the first divided difference with base xj by definition. For k equals 2, we have y of xj plus 1, xj plus 2 equals yj over w prime xj plus yj plus 1 over w prime xj plus 1 plus yj plus 2 over w prime xj plus 2. From this relation, again, by the rules of the divided differences, the second divided difference can be expressed using subtraction between two first divided differences. So in this case, this left hand side equals y of xj plus 1, xj plus 2 minus y xj plus 1 over xj plus 2 minus xj. Here wx is the product of these three terms, x minus xj times x minus xj plus 1 times x minus xj plus 2. Although I have not given you the generic proof of this expression, I have mentioned before that you might want to prove this using mathematical induction. For case k equals 2, you can verify, however, algebraically, that this expression, which is by the definition of divided differences, will be identical to this expression over here. Let's now continue to construct B-spline basis function using the Newton's divided differences. You must be wondering, how is it that these divided differences are related to the B-spline basis functions? You will probably see that now. This lecture is number 22, B-spline basis functions, the construction using Newton's divided difference approach. As I said before, we'll keep reminding ourselves that an nth order spline is C n minus 2 continuous. Coming back to the divided difference, let's consider a truncated power series function. F of t equals t raised to m minus 1 sub plus. Now this is an interesting function. For values of t greater than 0 or even equal to 0, t plus m minus 1 is equal to t raised to m minus 1. And for values of t smaller than 0, that is, for negative values of t, this function here is 0. You can think of this function getting truncated at t equals 0. Let's see how the plot of this function looks. This is how this truncated power series function goes as t increases. For values of t which are smaller than 0, this function is 0. For values of t greater than 0, this is a pure polynomial of degree m minus 1. You can see this polynomial is getting truncated at t equals 0. Now let's look at certain properties of this truncated power series function. Look at the value of this function, the first derivative of this function, the second derivative of this function up till the m minus 2th derivative of this function. Try to compute the derivative from the left hand side and the derivative from the right hand side. So for values of t greater than 0, since this is pure polynomial, the first derivative will be m minus 1 times t raised to m minus 2. The second derivative will be m minus 1 times m minus 2 times t raised to m minus 3, and so on and so forth. You know that. And if you evaluate these derivatives at t equals 0, you will find that all these derivatives will be 0 at t equals 0. So these are the right hand side derivatives, that is derivatives for t equals 0 plus. How about those for the left hand side? Well, the function is 0 for negative values of t, so all these derivatives will also be 0. So you would see there is a match in the derivatives. The first, the second, the third, up to the m minus 2th derivative, they match for values of t slightly larger than 0 and for values of t slightly smaller than 0. You can say that all these derivatives exist. And of course, you have position continuity as well. In other words, if you look at this function overall, this function is m minus 2 continuous at this junction point, t equals 0. For t greater than 0, this function is infinitely differentiable, and so is the case for t smaller than 0. How about the m minus 1th derivative at t equals 0 plus? So if m minus 1 t equals 0 plus is equal to m minus 1 factorial. That is the right hand side derivative. While if m minus 1 at t equals 0 minus is 0. So you would see that the m minus 1th derivative is not unique. In other words, this function here is not c m minus 1 continuous at the junction point. Let's look at this statement very carefully. An nth order spline is c n minus 2 continuous. Would this truncated power function satisfy this definition of a spline? Yes. So by the definition of spline, this truncated power function f of t equals t raised to m minus 1 plus is a spline of order m. So far, so good. Can we play with this truncated power function a little more? That is, can we play with the junction point here? Maybe yes. Or can we reflect this function about the y-axis? Again, maybe yes. Let's investigate. Now let's define another function, f of t sub j colon t, which is equal to tj minus t sub plus raised to m minus 1. Now this function, which is in the family of truncated power functions, is equal to tj minus t raised to m minus 1 for values of t smaller than tj. Remember that this number here, it should be positive. And this function is equal to 0 for values of t greater than tj. In other words, if this number here is positive, we get a pure polynomial of degree m minus 1, and if this number is negative, we get 0. How would the plot of this function look? Like so. We have a junction point tj right here. For values of t greater than tj, the function is 0. For values of t smaller than tj, this function is a pure polynomial. So we have changed the junction point, and we have also reflected this function about the vertical axis. Now, by the observations that we made for the parent truncated power function, which is this one, can we similarly say the same about this new function? We observe that f tj colon t, which is equal to tj minus t raised to m minus 1 truncated at t equals tj, is continuous at t equals tj, and that the derivatives up to m minus 2, they all exist and they are all unique. And so we would conclude that tj minus t raised to m minus 1 plus is also a spline of order m. By definition here again. Before we move further, let me go to the board and try to generalize this family here. This generalization will help us introduce Newton's divided differences along with this truncated power functions. So this is what I had mentioned before. F of tj colon t can be written as tj minus t truncated m minus 1, and this is equal to tj minus t raised to m minus 1 for t smaller than equal to tj, and this is equal to 0 for t greater than tj. Let me generalize this expression. Let me introduce another parameter called s. F s colon t equals s minus t truncated m minus 1, which is going to be equal to s minus t raised to m minus 1. If this number here is positive, that would mean that if t is smaller than s, equal to smaller than s, and then this number or this function is 0 if t is greater than s. So now this is a 2-parameter function. You can treat either s as a variable and t as a parameter, or vice versa. We'll see how we can use that when we are discussing divided differences a little later. This is where we introduce Newton's divided differences. We are going to be making a proposition. But this proposition is based on the following observation. A linear combination of the splines that we had seen before, considered over a knot span t0, t1, t2 up to tn, that is, some function psi of t, which is equal to summation r going from 0 to n of alpha r times tr minus t truncated raised to m minus 1. Here alpha r are constants, and the observation is that psi t will be a spline of order m. Would you agree with me on this? We have seen before that each of these terms for whatever tr is a spline of order m. So why not the linear combination of these would be a spline? The observation seems good, and based on this observation we say the following. A b-spline basis function is the mth divided difference of the truncated function f tj colon t, which is equal to tj minus t truncated raised to m minus 1. If you're finding it a little difficult to understand this, replace tj by s. Going back and repeating myself, a b-spline basis function can be seen as the mth divided difference of the truncated function f s colon t, which is equal to s minus t truncated raised to n minus 1. It would be a little difficult for you to believe this, but I'll try to show you how this is true. The idea here is to treat t as constant or as parameter and compute the mth divided difference for tj going from t sub I minus m, t sub I minus m plus 1, t sub I minus m plus 2 up till ti. Let me explain this procedure using the generalized truncated power function. Say if I want to evaluate this function at s0, I'll say that f of s0 colon t is equal to s0 minus t truncated raised to m minus 1. With this information implicit. Likewise, f of s1 colon t equals s1 minus t truncated m minus 1. Now, using the notation of the divided differences, I can consider this expression to be the 0th divided difference with respect to S0. Likewise, this is the 0th divided difference with respect to S1. Being consistent with the notation, I can write this thing as f within square parenthesis S0 colon t. 0th divided difference with respect to S. S0 here. Likewise, this can be written as f S1 colon t. Now, using S0 and S1, how do I compute the first divided difference? The first divided difference will look like within square parenthesis S0 comma S1 colon t. This is equal to f within square parenthesis S1 colon t minus f within square parenthesis S0 colon t over S1 minus S0. If I want to compute the first divided difference using S1 and S2, I'll have to write this thing as f of S1 comma S2 colon t. This is equal to f S2 colon t minus f S1 colon t over S2 minus S1. Now, using these two, how do I compute the second divided difference? So, the second divided difference will look like f within square parenthesis S0 S1 S2 colon t, and this would be equal to f within square parenthesis S1 S2 colon t minus f S0 S1 colon t over S2 minus S0. It would not be very difficult if you understand these divided differences for you to generalize and find what f S0, S1 up till Sk colon T would be. So this would be the kth divide difference, and if you have guessed it, this would be f of S1, S2 up till Sk colon T minus f of S0, S1, Sk minus 1 colon T over Sk minus S0. You would be able to generalize this further. Note that you don't have to start with S0. You can start with SR, for example. Now let's come back to our discussion on B-spline basis functions. So the mth divided difference can be denoted as f within square parenthesis T I minus m T I minus m plus 1 up till Ti colon T equals summation r going from 0 to m of Ti plus r minus m minus T truncated raised to m minus 1 over W prime evaluated at T sub I plus r minus m. And what we are saying as per our proposition is that this expression is equal to psi t, our B-spline basis function. It's kind of hard to imagine at this time, right? I will gradually show you why this is a B-spline basis function. Let's look at this expression on the left hand side. All I have done is I have replaced s's by t's. How many knots do you think we are using? We are using m plus 1 knots, or we are using m knot spans here. This expression is the mth divided difference of the truncated power function. You would have noticed that by now. This expression in the middle here is the algebraic form of the mth divided difference. You must be conversant with this expression also by now. Look at the numerator in each term in the summation here and try to relate this entire expression with this expression here. Alpha r times Tr minus T truncated m minus 1. What do you observe? You would note that each term by itself is a spline of order m. 1 over W prime evaluated at Ti plus r minus m are the constants alpha r. So in a sense, this expression is a linear combination. To be precise, a weighted linear combination of all splines of order m, and therefore this expression overall is a spline of order m, because each term is a spline of order m here. Let me expand this summation here and write psi t as T I minus m minus T truncated raised to m minus 1 over W prime evaluated at T I minus m plus T I plus 1 minus m minus T truncated raised to m minus 1 over W prime at T I minus m plus 1 up till the last term, which is T I minus T truncated raised to m minus 1 over the first derivative of W evaluated at Ti. You will have m plus 1 terms like these. I'm repeating myself here, but this would help both of us understand that since each term is a spline of order m, since each term has m minus 2 unique derivatives, the summation of all these terms will have m minus 2 unique derivatives, and by definition that would be a spline. Here Wt is the product of t minus ti minus m times t minus ti minus m plus 1 up till t minus ti. And as you know, w prime t is the first derivative with respect to t. If you are confused with the notation as to why we are using ti minus m plus 1 and so on and so forth here, and why t here, there is an easier way of resolving your confusion. Retain the knots as s I minus m, s I minus m plus 1 up till si, and then replace s by t. If you're not confused, don't worry about it. Now, why is psi of t a b-spline basis function? Do you remember this bell-shaped function? We will see here that psi of t essentially shapes like a bell-shaped function. I have borrowed this equation from the previous slide. Psi of t equals t I minus m minus t truncated raised to m minus 1 over w prime t I minus m plus t I minus m plus 1 minus t truncated m minus 1 over w prime t I minus m plus 1. The last term in the summation is t I minus t truncated raised to m minus 1 over w prime ti. We will show that psi of t is a b-spline basis function. In a sense, at t greater than ti. So in this figure here, ti is this knot here, and ti minus m is this knot here, and all the other knots are intermediate knots. So for t greater than ti, psi of t is equal to 0. We are looking at this region here. So the values of t here can be anywhere between ti and infinity. Why is that so? Why is it that for values of t greater than ti, psi t is equal to 0? Observe this expression carefully. In a sense, observe these truncated signs carefully. Here we assume that t I minus m, ti minus m plus 1 up till ti, they are all arranged in ascending order. So for values of t greater than ti, this expression here will be negative, and this truncated aspect of the function will make this term 0. Take a term on the left of this, ti minus 1 minus t truncated raised to m minus 1. Here again, t will be greater than ti minus 1, and so that term will be 0. So if you go back leftward, you would see that each term will have this number within the parenthesis as negative for t greater than ti, because of which this truncated sign will make the numerator in each term in this summation 0. We can generalize this. We can say that t I plus r minus m minus t truncated raised to m minus 1 for r going from 0 to m are all 0. So we have figured that in this region, psi of t is 0. How about for the region on the left? That is, how about for t equal to smaller than ti minus m? Psi of t will again be 0. And why is that? This would be a little difficult for us to understand in the first instance, but maybe we will be able to digest this as we move on. Let's go back to the same expression, psi of t. In terms of divided differences, what is this? This is the mth divided difference of a truncated power function of degree m minus 1. Keep that in mind. Let me repeat this for you. This is the mth divided difference of a truncated power function of degree m minus 1. Now, for values of t smaller than or equal to ti minus m, what do you think will happen to these truncation signs? They will all drop, because all these numbers within the parentheses in the numerator, they will all be positive. It is because of this that the truncation signs will drop, that the numerator will be a pure polynomial of degree m minus 1. I repeat, the numerator will be a pure polynomial of degree m minus 1. And you have seen this before. What is the mth divided difference of a pure polynomial of degree m minus 1? So here is what I have said. Psi of t is the mth divided difference of a pure m minus 1 degree polynomial. Let me pose this question again. What happens to the mth divided difference of an m minus 1 degree polynomial? The answer is, this is going to be 0. We have seen this before, and I'll discuss an example through which you can see this again. So we have figured that psi is 0 for t greater than ti, which is this range here, and psi is 0 for t smaller than or equal to ti minus m, which is the range to the left here. How about for values of t in between ti minus m and ti? That is here. We'll see that psi of t is standardized. That is, the area under psi t from ti minus m to ti, which is integration psi t dt from ti minus m to ti, which is equal to integration ti minus m to ti, the mth divided difference of truncated power function of degree m minus 1 is equal to 1 over m. It would be a little difficult for you to grasp this at this time, but we'll show you this very soon. We will show that this integration is equal to 1 over m using Peano's theorem, that says that m minus 1 factorial times g within square parenthesis ti minus m plus 1 up till ti colon t, where g could be any function here, and this expression is the mth divided difference of g, is equal to integration from ti minus m to ti of psi t times the mth derivative of g times dt. For those interested, they can look for the proof for the Peano's theorem. We'll simply use it to demonstrate standardization of psi of t. If you choose gt as t raised to m, which is a pure polynomial of degree m, the mth derivative of g is factorial m. Plug this information here. You'd also notice that the mth divided difference of t raised to m is 1. You can check this thing out for values of m equals 1, 2, 3, and so on and so forth. If you plug in this information here and this information here, we will have m minus 1 factorial equals m factorial integration ti minus m to ti psi of t dt, which would mean that integration psi of t dt with limits ti minus m to ti is equal to m minus 1 factorial over m factorial, which is 1 over m. To summarize, we have seen that psi of t is 0 for t greater than tj, psi of t is 0 for t smaller than tj minus m, in case tj happens to be the last nut, and the area under psi t in between the limits tj minus m to tj is equal to 1 over m. All we need to see is whether psi of t is non-negative in this knot span, and we will see that in the next lecture. Let's work on an example. Show using plots that psi of t, which is given by the third divided difference of a truncated power function f within square parenthesis t0, t1, t2, t3 colon t, which you would know is equal to summation r going from 0 to 3 tr minus t truncated squared over w prime tr is a quadratic B-spline with w of t given as t minus t0 times t minus t1 up till times t minus t3, w prime t as the first derivative of w with t, and assume that all these knots t0, t1, t2, and t3 are in the ascending order. We need to show that psi of t is a quadratic spline, that psi of t is equal to 0 for values of t not lying in the range t0 and t3. The fact that psi of t is non-negative is what we'll see in the next lecture, and that psi of t is standardized, that is, integration from t0 to t3 psi of t dt is equal to 1 over 3. So we know that individual truncated power functions of degree m-1 are continuous up to m-2 derivatives. Look at this definition here, and using that we can see that the third divided difference of a truncated power function of degree 2 is a quadratic spline. In terms of the knots t0, t1, t2, and t3, this is how the algebraic expression of the Newton's divided differences would be. Psi of t is equal to t0 minus t truncated the whole squared over w prime t0 plus t1 minus t truncated squared over w prime at t1 plus t2 minus t truncated squared over w prime at t2 plus t3 minus t truncated the whole square over w prime of t3. For t greater than t3, all truncated functions in psi of t are 0, and thus psi of t is 0. In a sense, all these numbers within the parenthesis are negative. Psi for values of t smaller than t0 can be written as this expression with all the truncated signs dropped. t0 minus t squared over w prime t0 plus t1 minus t the whole squared over w prime t1 plus t2 minus t the whole squared over w prime t2 plus t3 minus t the whole squared over w prime t3. Now this is a pure quadratic polynomial. The third divided difference of a quadratic polynomial tj minus t the whole squared should be 0, and we'll see that now. We'll compute the Newton's divided difference in the tabular form. We have the first column where we arrange the t values. We have the 0th divided differences f of tj colon t, the first differences, the second differences, and the third differences. We arrange the knots t0, t1, t2, and t3 in the first column. You know this. We arrange the values in the second column, t0 minus t squared, t1 minus t squared, t2 minus t squared, and t3 minus t squared. Here t is smaller than t0, and therefore we have dropped all these truncated signs. The first difference, using this information here and this information here, can be written as t1 minus t the whole square, this number, minus t0 minus t the whole squared over t1 minus t0. Now this is equal to t0 plus t1 minus 2t. Likewise, using the second row and the third row, we compute the first divide difference as t1 plus t2 minus 2t. In a similar fashion, using the third row and the fourth row, the first divide difference would be t2 plus t3 minus 2t. For the second differences, we will use this information and this information here. So t1 plus t2 minus 2t minus t0 minus t1 plus 2t over t2 minus t0, which will be equal to t2 minus t0 over t2 minus 20, and this would be equal to 1. Likewise, using this row here and this row here, the second difference would be t3 minus t1 over t3 minus t1, which is also equal to 1. Now remember this when we were discussing the Peano's theorem. The mth divide difference of t raised to m would be 1. This is something very similar here. And the third divide difference, of course, will be 1 minus 1 over t3 minus t0, which is 0. And this would be for all values of t smaller than t0.